Okay. So I think we did up to problem
Mhm.
5, right?
Yeah.
Problem 5 we did part A and part B. So now is part C.
Mhm.
So suppose M you are taking as V by U. So this is your rational number where U comma V is a solution to U square minus 2V square equals to 1.
Mhm.
Then you have to show that the other point what we found in part B.
The other point. Okay.
Yes. So we'll recall what we did. Other point in B has integer coordinates. Okay. So let us see.
Mhm.
So yes. So if you recall this part B,
Mhm.
so we found one solution, right?
Yeah.
So this was the other point, right? So here you are taking m equals to v comma u.
Mhm.
So m equals to v comma u. Then we have to show that this solution is an integer solution.
Okay.
Yes. So how will you show that?
So an integer solution would be something that is not really a rational number.
Yes, yes, it is. Yes, it is not. Means it is a rational number, but it is not of this form. Means it has to be an integer.
Which form is not?
Yes, means so in rational number we have fractions, right? So
Yeah.
means half to answer. Yes, that is not allowed. It is an integer.
Yeah. So I'm saying maybe we can demonstrate that this is not so it cannot be a rational number. We can
Yes, yes.
say
So
that.
I think it is not difficult. So the thing is, we'll start with this solution. So this is the solution what we had, right?
Mhm.
So let us just replace uh, v by u in this solution. M equals to v by u, right?
Okay.
So let us see what happens. So 2 v by u,
Mhm.
right? Then what you have? Right. So if you simplify, what will happen?
Uh, I mean, how you're going to simplify?
Yes. So we will try to simplify this means. So here, let me show you. So 2v square plus u square, right? Divided by u square. So
Oh,
this is the
okay, okay.
numerator, and 2v square
Yeah.
minus u
So you
square.
minus u square over u square.
Yes. And the
Okay.
second part will be 2v by u, that is there, and 2v square
So
minus
v
u square.
square minus 1 u square over u square. Okay.
Right. So here actually you can cancel these two things, right?
Mhm.
And here
Yeah.
also we can cancel u, and this u I can move up, right?
Mhm.
Right. So this will be 2v square plus u square.
2v square minus u square
2uv
equal to uv 2u and square minus.
That's correct. But in the starting, they have told that UV is a solution to this equation, right? So means this is satisfied, right?
Yeah.
So 2v square, so u square minus 2v square is 1, right? So we'll use that now. So u square minus 2v square equals to 1. So this implies 2v square minus u square. That will be minus 1, right?
Yeah.
Right.
Yes.
Okay. So this will be. So we'll just change these two things. So it will be just minus
B square minus U square.
minus 2uv, right? So these are integers, right? Because u and v I know they are integer. So
Yes, because U and B are integers, right?
right. So if I put this, so then this solution what you obtain, so that is an actually an integer solution, right? Fine.
I see. Okay, just replace.
Yes.
And
Just
then
it is
you
simplifying.
didn't find any division, like any divisor, and that's why. So there is no quotient, right?
Yes. There is no quotient. So yes. So the thing is, the rational definition is, so a rational number is of the form p by q, where q is not equals to 0, and GCD of p and q. So this has to be 1, right? So this is the definition of rational number. But if q equals to 1, then we'll say that it is an integer. Then p by q belongs to z. So this is the integer, right?
Okay.
So that's why they are saying that the solution has integer coordinates. Fine.
Yeah.
Okay. Let us move to part D. So part D, what they are saying is, so you can see that 3 2 is a solution to x square minus 2y square equals to 1, right? So 3 square is 9 minus 8. So that is solution, right?
398. Yeah.
So that is fine. So now they're asking that apply B and C repeatedly to find several more solutions to the same equation. So find more solutions. So other than this 3, 2, I have to find more solutions. Right. So x square minus 2y square, that is fine. Yes. So one more thing that I wanted to say. So here, this I can actually remove this negative sign because we are solving for x and y, right? But in the equation, we have this is our equation x square minus 2y square, right? So once we make it whole square, so this negative sign does not matter to us, right? So this is equivalent to actually u square plus 2v square and 2uv, right? Right. So I think this is the idea. So this is our starting uv. So starting with uv equals to 3, 2. So by part C, we have that u square plus 2v square, comma 2uv. So this is also a solution, right? Right.
Yep.
So let us see. Then what will be the next solution? Tell me. So if I put u equals to 3 and v equals to 2, what will be this thing?
So you're saying
Yes,
in
tell.
C. Okay, that would be 4, 8, 17.
Right. So this is 17 and this one is
12.
12. Right. So the next solution is your 17, 12. Okay.
Okay.
Now again we can use this 17, 12 as by new u, v. So 17, 12. And then find our next pair, next solution, that is u square plus again 2v square, 2uv. So what will be that? So this will be 17 square plus 2 times 12 square, 2 into 17 into 12.
Mm-hmm.
So what is the first one?
2a9.
Right. No. 17 square. Let me check once.
289.
I don't think. Check the calculation one. So 17 square, right? 17 square is 289. Yes, 17 square is 289, but I am asking the whole thing. Plus 2 into 12 square.
577.
Right, 577. And the second one is 408. So this is my using. So like this, I can find infinitely many solutions, right? I can go on like this, right?
But wait, that is because. But I mean, how do you know?
Yes, still.
How did you know that the solutions are of the form of u squared plus 2v squared, comma 2ub?
Yes. That follows from part B and C, right? Because what I showed is if xy is a solution, right? Here,
Yeah,
then this is also a solution that I showed, right? This is also a solution to that equation.
that is the third point.
Yes.
That is a point that intersects
Right.
the
That is the
curve.
point that intersect, right? So this means this is a solution to that equation, right?
Yeah.
Right. So now,
Mm-hmm.
if I take m equals to u by v by u, where uv is a solution to this equation, right? We simplified
Mm-hmm.
this thing. So since m is a rational number, I know that m satisfies this thing. So m has this form v comma u, v by divided by u. So once I put it into this form, then I get u square plus 2v square comma 2uv,
Mm-hmm.
right? So that also you can easily verify from here. So what is happening is, so let us check. So if we put u square plus 2v square in the equation, so I have this whole square minus 2 times of 2uv whole square, right? So this has to be
Mm-hmm.
equals to 1, right? If this is a solution to the equation, right?
Mm-hmm.
So let us verify whether it is working. So it's u power 4 plus 4 u square v square plus 4 v power 4 minus
Mm-hmm.
8
U square v square.
v square, right? So this will be u power 4 minus 4 u square v square plus 4 v power 4, right? So this is
Yeah.
nothing but u square minus 2v square whole square, right? But since u comma v is a solution to that, I know that u square minus 2v square equals to 1. So this is also 1.
I see.
Okay.
So this is like a parameterization as well, right?
Yes. Some sort of representation. So actually, once you find one solution, you can generate infinite solution from that. So from this solution, I can use that if I know u comma v is a solution to this equation, I know that u square plus 2v square comma 2uv, this is also a solution. So I start from any particular solution, I can generate infinite solutions like this.
Okay, repeat that last part. So since you
Yes.
found a point, so okay, so first you intersect the point, intersect the line with the curve, and then from there
Yes,
you find a solution
right.
u squared minus 2v squared equal 1, but that's like arbitrary, right? How do you know that that is a solution?
No, that is the thing what we derived from part B and part C, right? This is what we derived, right? Okay, let me quickly recall. So that's why, right? So first of all, I started with this equation, right? This is my
Mm-hmm.
equation, and I know that 1 comma 0 is a solution, right?
Yes.
Okay, so then we use our usual trick. We draw a line L that passes through 1 comma 0 and have slope n. So m is a rational number,
Mm-hmm.
right? So it will intersect this curve at another point. We want to find that point, right?
Yes.
So this is the equation of the line, and it intersects this curve at another point. So we just find by substituting that, we find that the equation of the solution, or the point at which the line L intersects the curve again, is given by this thing, right?
Mm-hmm.
So you already know that this is a solution to the equation x square minus 2y square equals to 1. Fine,
Yes.
right? So now, if I take m to be our rational number, where it is v by u, and uv is a solution to this equation, then I showed that this point where the line again intersects the curve, this is nothing but this point, u square plus 2v square comma 2uv.
Okay.
Okay,
Yeah.
so that is then this sets the stage, right? So if I know that u comma v is a solution, I have proved that u square plus 2v square comma 2uv is also a solution.
Mm-hmm.
So that is now what we are using in part D to find an infinite set of solution. Starting with a single solution 3 comma 2, I can actually generate infinite solution like this. I can go on continue like this.
Okay. Okay.
Fine.
And these are already square triangular numbers.
No, what is quadrangular numbers?
No, triangular.
Yes, yes. Triangular numbers is the next thing.
So
Yes,
here
square
it says,
triangular numbers, right? So now we have to use these solutions to find additional example of square triangular numbers, right?
okay,
Okay. So how will we get that? So that is the idea.
square. So we need to equate m square equal to m plus m is 1 over 2.
Okay.
Mm,
Okay. So if you remember,
mm,
we want square triangular numbers, right? So we want that m square to be equal to n into n plus 1 by 2, right?
yep, yep.
So this is the property of square triangular number.
Yeah.
Okay. So now let us just simplify. So 2m square is nothing but n square plus n, right?
Yep.
Okay. Right. So if you remember, we to I want to complete the square this portion, so I multiplied by 4. If you remember, so it is 4 times 2m square equals to 4n square plus 4n. Then I plus 1 and minus 1. This I did, if you remember.
Mm-hmm.
So 2n plus 1 whole square minus 1.
Okay.
So if I send to the other side. So I have 2n plus 1 whole square minus 2 into 2m square equals to 1, right?
Mm-hmm.
So now you can see that this is actually matching with our equation, right? U square minus 2v square equals to 1, right? So that is of this form, right? So if I take this part as u and this part as v, then it is matches to our original equation, right? U square minus 2v square equals to 1.
UB. Wait, say that again.
No, what I'm saying is I want to find square triangular numbers, right?
Yeah.
Okay, so I just simplified and got this equation, right?
Mm-hmm.
Okay, so now if I so this 2n plus 1 if I replace by u and 2m if I replace by v, so then it is nothing but this original equation, right? U square minus 2v square equals to 1.
Mm-hmm.
So this is the idea.
U square minus. Okay.
Right,
So 2n plus 1 is equal u
right,
and 2n is equal v.
right. So that will help us to generate more square triangular numbers. So what we will get is so we set uh, 2n plus 1 equals to u. So this give me solution for n. So n equals to u minus 1 by 2 and 2m equals to v. So this gives m equals to v by 2, right? So
Mm-hmm.
I know that there are infinitely many solutions for this particular solution, right? U square minus 2v square equals to 1. So this I know, right? So for example 3 comma 2 is then we have 17 comma 12, 577 comma 408. Like this I can create infinitely many solution, right? Now for this each u comma v I can create m and n, right? Because I can define n to be u minus 1 by 2 and m as v by 2.
Okay.
So this will give me square triangular numbers, because once I have m and n,
Mm.
right?
Mm-hmm. Yep.
So this is what they're asking. Is it clear?
Mm. Mm-hmm. Yeah.
Fine.
Yes.
Okay. So next part is yes. So next part is actually the same thing they're asking. So this procedure leads to infinitely many different square triangular numbers. So that is fine, right? Because I know that there are infinitely many solutions to u comma v. So each u comma v will generate me a new solution, right?
Mm-hmm. Yep.
So that is fine. So E is fine. And part F is, I think, similar. Prove that every square triangular number can be constructed in this way. So yes. So this is a little. We can skip this now because it is not easy. We'll need some more tools to solve it. Okay.
Okay. Okay.
Okay. So now we can move to the next chapter, chapter 4. Fine.
Yep.
Okay. Sum of higher powers. And the Fermat's last theorem. Okay. So we know this type of equation, right? So this is the Pythagorean equation. The next natural question is, do this type of equations also exist? Means, does there exist integer solution to this equation? And a power 4 plus b power 4
This is
equals to 0.
already the next. The next chapter, right?
Yes, next chapter.
Okay, sum of 5 powers, right? Okay.
Right. So the first equation is well known to us: a square plus b square equals to c square. So this is the Pythagorean equation.
Yeah, Pythagorean
But
equation, right?
but the natural question that comes into mind is whether if we take higher powers, so does this type of solution exist? So a cube plus b cube equals to c cube if I take, or a power 4 b power 4 equals to c power 4. So does it have integer solutions? So that is the natural question. So in general, there was a conjecture that was given by Fermat that this any n, if I consider a power n plus b power n equals to c power n, where n is
Mm-hmm.
greater than equals to 3, so this does not have a solution. Means integer solution, of course, does
Mm-hmm.
not have solution in positive integers.
Okay.
Does not have solution. Right. So this was proved later. So that is the Fermat's last theorem. Okay. So then, okay, I think most of them after that they have told some history about that mostly. 1 minute, let me check. Okay. Okay. Let us go to directly exercise because there is nothing in the chapter actually. So exercise
About
you
what?
can go to part 2 because
Part, part two.
the second exercise.
Part two, you
Yes, part
mean,
1 is also some history they are saying.
right?
Okay. So let us see part 2.
Okay, what is part two? Where is part two?
Yes, that is on page number 27 in the book, page number.
Okay, yeah, I can see it.
Got it?
Yeah.
Right. Okay. So it is saying that the equation, right. So that is what we learned. So a cube plus b cube plus c cube has no solution in positive integers, right? So, so now that's slightly changing the equation. So now if I take a cube plus b cube equals to c square,
Okay.
right? And we have c is greater than equals to b, greater than equals to a, greater than equals to 1. So we have to find
Mm-hmm.
that if this equation has solutions or not. Okay.
Okay.
Right. So the first part they have given one solution. So that is 2 comma 2 comma 4 equals
Find
to,
3 more solutions.
right. So first let us verify whether this is working or not. So 2 cube plus 2 cube.
Okay, here.
So this is I think
Yeah.
16, right? So this is 4
Mm-hmm.
square. So this is a solution. So you have to find 3 more solutions. So how will you do that?
I don't know. How would you that?
So they have given some hint, right?
Mm-hmm.
So the hint is so if I have, okay, let us use that hint. A comma b comma c equals to xz, yz, and z square, right?
Yeah.
So if I just put them into the equation, what I have,
So again, this is like a parameterization already, right? Giving
yes,
you this.
yes. So if I simplify,
Mm-hmm.
equals to z power 4, right?
C4, okay.
So right, so I can cancel z power cube from both sides.
Then Z
So I
cube.
have x cube plus y cube equals to z, right?
Uh-huh. Yeah.
Okay. Right. So if I get So if I choose z to be x cube plus y cube, then this is a solution, right? Because we are putting them into the required solution. So what I have is a comma b comma c equals to actually x into x cube plus y cube.
Yeah. Okay. So you are getting rid of
Right. We are reducing one variable,
one variable more.
y cube whole square.
Okay.
Right? So now I have freedom to choose any x and y, right? So if I choose any x and y, so I know that this will be a solution, right? So let us check first few choices. So for example, they have taken 2 to 4, that is fine. What should I take next? So if okay, so I think 1 minute. Yes, so if x equals to 1 and y equals to 1, then I think we have the 2 to 4, right?
2,
This is the
2,
solution.
4, 1, 2, x and y 1. Yeah, seems
Right.
like it.
So now let us change it. So suppose x equals to 1 and y equals to 2. Then what will be the solution?
A9, A, A9,
9.
9, 9, 18,
Right.
81.
Right. So maybe let us take one more. So suppose x equals to 2 and y equals to 2.
Okay,
2 cube 8, 8, 16. 16 to 0. 32, right?
32,
Second one is also 32.
64. Oh, no, it's just, yeah, same.
256, right?
Yeah.
Yes. So this is so this gives us some sort of parameterization, right?
Yep.
So if I choose x and y, so now I have the freedom of choosing x and y. Then I know that this ABC will always be a solution to this equation, right? Fine, right?
So wait, but what's the question?
Yes. Question is they gave one solution and told to find 3 more solutions.
So we're just replacing. So we use the hint and then we replace into the general equation
Yes.
and then we remove one variable.
Yes.
Okay.
Fine.
And then any combination x, y would may work.
Yes. So x and y, any combination will work.
Okay, fine.
Right. Now let us see part B. So part B, they are saying, so ABC is a solution to star. That is our original equation. That is a cube plus b cube equals to c square.
PQ, C square.
And n is any integer. Show that n square n square b, and n cube c is also a solution. Yes, I will show that.
That is a solution. But in this case, n is just any number above 2.
Yes, tell.
So Maybe we can just start by replacing ABC in the equation,
Right.
and then from there,
Right. So since I have capital A, capital B, and capital C,
mhm,
so this is satisfying. Then
yeah,
then you have to verify that this is a solution.
yeah, we need to arrive from above to below.
Right. So how will you do it?
So, I mean, let's start by multiplying by n. No. Um,
Yes. So what do you have to show? So you have to show that uh, n square a whole cube.
mhm. Yeah.
So this you have to show that whether it is equal or not, right? So
Yeah.
if I start with the left hand side, yes. So this is equal to
N to the 6
hmm,
parentheses a cube plus b cube.
right.
Now we can simplify n to the 6.
Yes. How will you do next?
That would be a to the cube plus b to the cube is equal to a cube plus b cube.
No. After this, what can I write?
Oh, I see. This after this, I mean this is going to be equal to n cube c to the square, right?
Right. Right. So now we can use this condition. So
Oh
this
yeah,
I
you
can
can use the
use.
other one, right? N to the
So
6 equal to
c square, right?
c
So
square,
now
right?
I can write in this also. So this gives my RHS, right? So hence it's
Yeah.
proved that that this is also a solution, right? Fine.
So the second line is also solution
Right.
because n to the 6. Okay. Yeah.
Fine.
Yep.
Okay. Hmm.
Yeah. It's good.
So next, what the saying is, write down four different
But
primitive solution.
it also says for any n greater than 2. So we didn't take into consideration that, or
Okay. Let us check what you're saying. So
any greater or equal than 2.
right. So the thing is that we will say solution ABC to be primitive if it does not look like this thing, right? Because primitive is their GCD should be one, right?
Yeah.
Right.
Yes.
So
GCD.
here the GCD is n square, right? Because uh, you can take GCD common, is it at least n square, right? And if n is greater than equals to 2, then it is no longer a primitive, right?
See, if n is greater or equal to 2, it's not a primitive because yeah, it's going to have a divisor, right?
Right, right. We have a common divisor, right?
So, but if n is not greater than 2, so n will be 1 or 0 always.
Yes. So yes, yes. So they are saying that when it is not a primitive thing. So the primitive thing is that when we cannot take out a common factor out. So that is the idea.
Uh-huh.
Okay.
It does not look like. Yeah, so I mean, so n will be always 1 or 0 in this case.
Yes, 0 it is not possible. Yes, n is 1 in this case. Means n will be 1 because then we cannot take out a factor. So yes, so you'll actually get an idea if we compute a few more examples. So for example, okay, let me think.
Mhm.
Yes. So for example, this is not a primitive, right? Because what I can do here is, so it's 9, right? So so I can take out, right? So I can take out 3 square times 1. This is 3 square times 2, and this is 3 cube times 27 into 3, right? Right.
Yep.
So this is not a primitive, right?
That is not a primitive because yeah, and because n is either 2 or 3.
Right, right. So here the definition of primitive is that, so that it is not of this form. Just to let me write down, then you'll understand. So we will say a solution ABC to that equation, that a cube plus b cube equals to c square is primitive
Mm-hmm.
if it does not look like.
Isn't that the same as saying okay.
N cube c for some n greater than equals to 2. So that is the definition of primitive here. So here
Okay.
actually, so for example, if I consider the solution 2 comma 2 comma 4, right? So this is a
Okay.
solution, right? So but this is a primitive solution in this definition sense, because it is not of this form n squared a plus. You cannot factor out n like this from this solution. So this is a primitive
I
solution.
see. Because n in this case will be always
N is
1.
1 here, right?
Right.
But the second solution, what you got is 9, 18, and 81. So this is not primitive because I can factor n as 3. I can take n as 3.
Mm-hmm.
Okay.
Yeah. Yeah. So this is primitive only with this restriction.
Right, right.
Okay. Okay.
Right. So they in the part C they are asking to find primitive solutions. So actually, if I check the third one also, third one is 32, 32, and 256, right? So let us check. Yes, tell me whether it is primitive or not according to this definition.
Okay. So that would be 2 to the power of 5.
Yes,
2 to the power of 5.
and
2
256
to
is I
the
think
8.
2 power
2
8,
to
right?
the 8. 2 to the 8. But I mean, you can express it like 2 to the square multiplied by 2 to the cube.
Right. So what we can take out as n? Can you tell me? So n is
2 to the square.
4. What is 4 cube? 4 cube is uh,
4, y4 cube, y4 cube.
yes, yes. So what I wanted to say is, so if I take 4 squared times 2, right? Like this I can write.
For the first one. Oh, yeah.
Right.
Okay.
So this is 4 squared times 2 also. I want to write 4 cube times something, right? So 256 divided by 4 cube will be
1. What did you say? Oh, no. Uh, 4. Multiplied by 4.
right. Uh, right. So yes, so this is also not primitive then, right?
Because it is the same.
Right. So here
Because
actually
of
n
the
equals to
order.
4, right? So
Yeah.
this is my n. Okay, so they are asking to find a few more primitive solutions. So let us try to find. So this was x we took x equals to 2, y equals to 2. So if I increase y equals to 3, then what happens? So
Y3.
x2, y3. So we have to use that parameterized equation. So this is our equation, right? Let us copy. Right, then what will be our ABC?
Okay. 8, 29, 35, 70.
70, right?
Yeah.
70, then
105.
right, 105, and the last one is 1225. Okay, let us check whether this is primitive or not. Please try to do it.
Okay. In a square, right? That would be it is not possible because 70 is 2 multiplied by 5 multiplied by 7.
Right.
You
So
cannot do it.
5 multiplied by 7. Yes, yes. We cannot find any square factor, right? Yes. So this one is a
Right.
primitive.
So if only one does not have that, it's already a primitive. What if let's say 12, 25, it is n to the cube?
Yes. Okay.
Okay.
What about 3 comma 3? Means x equals to 3 and y equals to also 3.
Okay, 3,3.
So 3 cube is 27. 27 into 2 is
160.
one. How much?
54 multiplied by 3, right?
Right. 54 multiplied by 3, 162. Right.
162, right.
This is also 162. And the last
162.
one is 54 square. 54 square, let me calculate. So
54
54
multiplied by
times
54.
2961. Sorry, 2916. Yes. Is it primitive? So can we factor out? So what will be the factorization of 162?
9 to the square multiplied by 2. So there is a 2 over there. You cannot 9 to the square. Yeah, 3 to the 4, right? 3 to the 4 multiplied by 2.
So here you're saying 9 square into 2.
Yeah, which is 3 to the 3 to the 4.
Yes, yes, that is fine. We can write 9 also. But the thing is, can we factor out 9 cube from here? So that is the idea.
Yeah, we
So
need 9 cube. Isn't that, sorry, what was the condition? N to the 4, I think it was.
the condition is no. N square, and n cube.
N square, okay. Let's see. N square. Let's
Yes.
see.
So the factorization of 2916 is 2 square into 3 power 6, right? So that is nothing but 2 square into 9 cube, right?
Mm-hmm.
So this I can write actually as 9 square into 2, 9 square into 2, and 9 cube into 2 square.
Yeah.
So here n equals to 9. So this is not primitive.
Mm-hmm.
Okay.
Yeah.
So this is
Not.
the idea. So so here they have defined one condition of primitive, that if it of this form and n is greater than equals to 2, then we will say that the solution is not primitive. Okay.
Yeah,
Otherwise,
I
it is
got it.
primitive.
Yes.
Fine.
Mm-hmm.
So similarly, I think you can find out other primitive solutions also. I think the next
Yeah.
one will be also primitive. So if I take x equals to 2 and y equals to 4, I think that will also work out. Okay.
Mm-hmm. Yes.
So next what they're saying is, okay. So next they're saying is that if you can see that 2 comma 2 comma 4 is a primitive solution that you saw, right?
Yeah.
So 2 comma 2 comma 4 is a primitive solution, but 32 comma 32 comma 256 is not primitive, right?
It
Also
is
we
not.
saw that 162 162 and 29C16, that is not primitive. So part D they are asking is, find all primitive solution where these first two components are equal. So that is the part D.
Mm-hmm.
Okay. So is the question clear?
Yeah. So A and B are the same.
Yes. So find.
But how do you want? How are you going to express it? How do you
Yes,
want
that
to
is a
express when function?
such that A equals to B. Alright. So if A equals to B, then what is happening is, so our equation is actually get reduced, right? So I have A cube plus B cube equals to C square. So if A equals to
Mm-hmm.
B, then I have 2A cube equals to C square, right?
Mm-hmm. Yeah.
Right. So this implies that C has to be even, right? Otherwise,
So
we
it has
don't have
to
any
be
choice, right?
even, right?
Okay. So suppose C equals to 2 times some C1. Okay. So if I substitute again, 2A cube 2C1 whole square,
Uh-huh.
2A cube times 4C1 square. So that gives me A cube equals to 2C1 square,
To see
right?
one square. Mm-hmm. So A to the cube is also even.
Right. Again, we can say that A is again even. So from here,
Mm.
A is even, and let A equals to 2 times A1, right? So again, if I substitute, so I will get 4A1 cube equals to C1 square, right? Because I will cancel 1 2.
For wait.
So
Yeah.
8A1
Okay.
cube, right?
You cancel it to the right.
So this again says that C1 is even.
Yep.
So let C1 equals to 2C2. So if I substitute again, so it's 4A1 cube equals to 4C2 square. So this gives one A1 cube equals to C2 square,
Mm-hmm.
right? So what I got is, it is only possible if a number, it is a both perfect cube and a perfect square, right? So what I get is, so A1 is actually equals to n square, and C2 is actually n cube. If I have this thing, then only I have A1 cube equals to C2 square, right? For some integer n,
Mm-hmm.
right? But
Okay.
what is our original A? So A is nothing but 2A1, so it's 2n square, and C equals to what I take is 2C1, but C1 I took as 2C2, so it is 4C2, right?
Mm-hmm.
And C2 I took is n cube, so 4n cube, right? So the primitive solutions to the equation will look like 2n square, 2n square, and 4n cube.
Mm-hmm.
So that is for any integer n or natural number n, right? So if I take n equals to 1, then I got our first solution 2 comma 2 comma 4. So similarly I can put other solutions to get infinitely many solutions or primitive solutions to that equation.
Mm-hmm.
So this is fine.
Yeah. So, but you invented n over there, so n is not part of the
No, n is just we want to give a general solution, right? So n is just a part of
general
it.
solution. Right. Okay, for n that belongs to natural. Okay.
Right. So I can generate infinitely many solutions like this. So our first solution was 2 comma 2 comma 4, right? So that is when I put n equals to 1. Similarly, if I put n equals to 2, I'll get something like that.
Mm-hmm.
Okay.
Yep.